Now we can begin to further discuss about Lesson 9, 1.4.2, the spatial motion of systems of particles and rigid objects. So a system of several objects, if each object can be approximately treated as a particle, so they become a system of particles. When the differences in the motion of each point is not neglectable, it is decomposed into a series of infinitely small parts, each of which can be treated as a particle, and the object becomes a system of particles. So you can see if we have 1, 2, 3, 4, 5, we have a bunch of particles inside, and each are doing different spatial motions. We can treat it as a whole entity that it was a system of particles. The motions of the intermediate contour lines and the plane curve can be classified as spatial cases of plane curve motion, and the motion of each particle can be called spatial curve motion. The free movement of each particle in space is determined by 3 independent variables such as x, y, and z, which are called 3 degrees of freedom. For a system of n particles, if each particle can move freely, the motions of the system is determined by 3n independent parameters, such as xi, yi, zi. So we can think of one particle, it can move 3 directions, x, y, and z. Thus, it has 3 motion of freedom. And also, if each particles are located in this space, each has 3 degrees of freedom. Thus, if we have n particles, we have 3n degrees of freedom. So the degrees of freedom is also an indicator of how freely those systems can move. So we can name such as xi, yi, zi indicate each component of the movement of each particle, where I equals 1, 2, n, that can be any number between 1 and n. So the larger n is, the more difficult it is to describe the movement of the system. A rigid object in special system of particles whose distance between 2 points is constant. So that means a rigid object, any point in this rigid object have a distance d, and whatever this object move, like in all, the distance between those 2 points will never change. So rigid bodies are 3-dimensional. In rigid body, 2 point A and A2 are taken, A1 and A2 are taken, and their respective motion parameters are set to x1, y1, z1, and x2, y2, z2. Because the distance between A1 and A2 does not change, what does this tell us? This tells us that x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared equals L12 squared, which is a constant. That's just the distance between those 2 points. L12 simplified is d, the distance between the point A1 and A2. Thus, we can see, because of this restraint, the independent parameter is reduced to 5 numbers. So in rigid body, the point A, which is not collinear with A and A1, is taken. So we got another point A3, which has an coordinate x3, y3, and z3. Thus, we can write another two equations, x3 minus x1 squared plus y3 minus y1 squared plus z3 minus z1 squared equals L13 squared is a constant, and x3 minus x2 squared plus y3 minus y2 squared plus z3 minus z2 squared equals L23, which is also a constant. This distance is L13, and this distance is L23. So, because all those combined together tells us there was only one parameter that is independent. So any other point in this rigid object, suppose we have another point AN, and its parameter xn, yn, zn have the restraint function as xn minus xi squared plus yn minus yi squared plus zn minus zi squared equals lin squared is a constant, where lin is the point an to the point ai, the distance between them. And thus we can see this gives us three equations about xn, yn, and zn. That tells us that all the three parameters are all dependent. Thus, we can see that three-dimensional rigid objects move in the space. Its independent parameter is always 6. Or, in other words, the number of its degrees of freedom is 6, and the mathematical treatment is generally simplified. So it is not difficult to understand that the plane-shaped rigid object, such as a thin plane, still has 6 degrees of freedom. But the straight-shaped rigid object, such as a thin bar, only have 5 degrees of freedom, because all the points you can take are all from the same line. So there is no parameter of the distance that is perpendicular to that line, because there was nothing of that rigid object that exists except for this same line, so there shouldn't be any point in outer space. So it only has 5 degrees of freedom. So a simple motion of a rigid body is translation, where the line between any two of its points remains parallel to itself. So, for example, we have a sphere, large sphere, with diameter A2, A1. Oh, this is not a best sphere. And it has a radius r. So we have another small sphere with radius little r on top of it, which has a1 prime, a2 prime. So we can see if the little sphere a1 prime, a2 prime experience a translation, it means it does not have any rotation, does it not turn, so in each position it's all the same position. The way it faces does not change. Since the direction of its face does not change, any movement of this rigid object can be described with one point of this object. What does this mean? This means that as long as we know what is one point of the whole object is located, we can know how the whole object is placed in the space. Because the distance of this point with all the other points in this rigid object does not change, and the direction of its face does not change, so we know where the whole body of this sphere is. What does this tell us? This tells us that the degree of freedom of this rigid object during translation is decreased to 3. But there is also like special cases where translation is constrained to one plane. If every point of this sphere, the motion is constrained to one plane, the degree of freedom is thus reduced to 2. Another type of motion of a rigid object is rotation. It can rotation around a certain point of a body. For example, we have a plane, this is our z-axis, and we have an object that is rotating in this space. If the point of the body is not, one point of the body is not moving, it is called a fixed point rotation. There are 3 degrees of freedom to rotate about a point. For example, this can experience a rotation around the z-axis, and that is called precession. Also, it can rotate this way. So this is called nutation. Last but not least, it can self-rotate. So this is simply called double rotation. Thus, all rotation around a fixed point can be decomposed of precession, nutation, and double rotation. So those also can cause self-rotation or whatever. So we can see this is 3 degrees of freedom. Combined of the 3 degrees of freedom of the translation, we can see that a rigid object has 6 degrees of freedom in all when it's moved freely in the space. An ideal linear rigid object loses only 2 rotational degrees of freedom because it has no body and its rotation can be measured. If we have a linear line rigid object with point P1 and P2 on this object, and the P1, P2 line of all points on this part are fixed, forming a fixed axis. Rigid rotation is the rotation around the fixed axis. That means all it can do is rotate along this axis. So windmill rotation, the rotation of a door, or the rotation of a ceiling fan are fixed axis rotations. Just fixed axis rotations, only 1 rotational degree of freedom because it can only rotate this way. When the rigid object makes any motion, a point C can be chosen as well. And the motion of the rigid object is divided into translation with C and rotation around C. Suppose we have a rigid object, we can choose a C, and all movement of this rigid object can either be decomposed as the translation movement or the rotational movement. For example, we have the Earth in the center and we have the moon. We can choose one point C on the moon in the center of the moon. and the rotation of the Moon about the geometric axis passing through C. The period of the circular object around the Earth is the same as the period of the Moon's rotation around C, so that the Moon is shown in this figure with always one face towards the Earth. One half of the sphere is always facing the Earth, and the other half of the sphere is always facing back the Earth. That's the diagonal area in the figure. In the decomposition of rigid body motion, although the reference point of translation can be chosen arbitrarily, it will always be chosen conveniently according to the specific question. For kinematic reasons, the central point is often chosen as the reference point of the motion. For kinetic reasons, it is preferable to choose the center of mass as the reference point for motion. For example, the pure rolling of a bicycle wheel on the ground is usually decomposed into a flattening motion with center of the wheel and the rotation around the central horizontal axis. Many rigid bodies, there is no material distribution of the rigid body at the center, as in the cases of a bicycle wheel. If a rigid body is expressed as a flexible object that can extend infinitely, the density of the extension side is equal to 0. Or any point which remains relatively stationary at times with points of the flexible object may be owned by the rigid object. Then a rigid object can still be a point of a rigid object even if there is no material distribution of the rigid body at its geometrical center.